This is Mr. Alexander again, and we are going to finish up the Unit 5 test review here, starting on number 10. Should go pretty quickly. For the equation y equals 2x cubed minus 4x squared plus 3x plus 4, identify the number and type of solutions. The easiest way to do this is to simply graph it and see how many times it crosses the x-axis. So that's exactly what we're going to do here. I'm going to go to my calculator, and I'm going to type into y equals the equation that was given to me, 2x cubed minus 4x squared plus 3x plus 4. And I'm just going to graph this thing. And I'm going to see what it does. I'm zoomed out a little bit, so I'm going to zoom in the normal way. And what we've got here is we can see this thing crosses the x-axis exactly one time. Right there. It's got one x-intercept. So what that means is this thing has one real solution. And you might be tempted to say that that's it. But because this thing is a cubic, it has three solutions. It just so happens that only one of them is real. The other two are complex. So these two numbers are always going to add up to 3. You figure out how many real solutions there are by how many times it crosses the x-axis. The remaining solutions must be complex. It's as simple as that. Number 11 is pretty simple as well. What's the domain of this cubic function? What's the range? I don't even need to graph this thing. I don't need to do anything with it. I just need to remember that the domain for every cubic function is all real numbers. Same with the range. So no matter what you do to the function, no matter how you transform it, no matter what you do, the domain and range of every cubic function is always all real numbers. So remember that. Number 12. Describe the transformations from the cubic parent function to y equals negative 3 times 2 times parentheses x plus 4 parentheses cubed minus 1. I'm counting 1, 2, 3, 4, 5 transformations. Let's list them all. First transformation is that negative right there. That makes this thing a reflection across the x-axis. The next one, that 3, that makes it a vertical stretch, which I'm going to abbreviate as VS, by a factor of 3. This 2 right here is the horizontal, but it's a horizontal compression because it's greater than 1. Remember, inside the parentheses is counterintuitive. So it's a horizontal compression by a factor of 1 over b, or 1 over 2, because our b value is 2. This plus 4 makes it go left 4, and that minus 1 makes it go down 1. So that's all there is to it there. Similar question here, but deceptively difficult. Describe the transformations of the cubic function to y equals negative 2x plus 4 cubed minus 2. Well, the first thing you need to realize is this is not in transformation form yet. We need to get it there. There can't be anything in front of that x to be in transformation form. So I'm going to rewrite the function. I'm going to keep the negative, but I'm going to factor out this 2. And when I do that, I'm going to have x plus something inside the parentheses here. And so 2x divided by 2 is x. 4 divided by 2 is 2. So this thing has 4 transformations. 1, 2, 3, 4. The negative is a reflection across the x-axis. That 2 is a horizontal compression by a factor of 2. Or sorry, 1/2, because it's 1 over b. Now it's going left 2, not left 4. And then it's going to go down 2 as well. A lot of 2's in that problem. Alright, let's talk about number 14 next. 14. On the graph below, they identify the coordinates of the inflection point, the relative max, and the relative minimum. Well, here's your relative minimum right here. And the reason we call it a relative minimum is because if you just said it was a minimum, that implies that it's a absolute minimum. And as you can see, this thing has no absolute minimum, or maximum for that matter. And the coordinates of this relative min are 0, -2. The relative max is right there. I've already put out the coordinates for you, so we just need to put relative max. And again, it's not an absolute maximum because this thing goes up forever. There is no absolute max. Now the inflection point is always going to be in between the relative min and relative max. Exactly in between. In fact, it's right here. I'm just going to call that the IP, the inflection point. And the coordinates for that are just 1, 0. And so that inflection point is always going to be in between the relative min and relative max. Okay, we're almost done. Number 15 says, write a cubic equation which has been reflected, vertically stretched by a factor of 7, shifted 2 units down, and shifted 3 units left. So every equation starts with y equals, or f of x equals for that matter. It's been reflected, so I've got a negative. It's vertically stretched by a factor of 7, so I'm going to put a 7. There's no horizontal compression or stretch, so I can go right into my x. Shifted 3 units left, so that's going to be plus 3. Don't forget your cube to make it a cubic. And then 2 units down, so minus 2. Is that it? That's it. It's just that simple. Write the equation for the cubic parent function and graph it below. Well, that's just y equals x cubed. That's the cubic parent function. The inflection point is right there at 0, 0. At 1, it's at 1, and at 2, it's at 8, because 1 cubed is 1, and 2 cubed is 8. At negative 1, it's at negative 1, because negative 1 cubed is negative 1. And at negative 2, it's at negative 8, because negative 2 cubed is negative 8. So this thing goes up forever like that, and down forever like that. That's the cubic parent function. So number 17, we're supposed to identify the x-intercepts. There's only one, 0, 0. And it's also true the y-intercept is at 0, 0. The domain of this thing? Well, I told you the domain and range for all cubic functions are the same. Simply negative infinity to positive infinity. The inflection point, right there, 0, 0. Relative min and relative max? Well, whereas over here, this thing had some clear humps, the cubic parent function doesn't. So this thing actually doesn't have any relative mins or maxes. But it does have symmetry. It's not symmetry in the way we conventionally think about it. It's not like we can cut a line down the middle of it and it's the same on both sides. No, this thing has a rotational symmetry. In fact, its symmetry is rotational by 180 degrees, which means if you took this thing and you twisted it 100 degrees, it would look exactly the same. It doesn't matter if you do it clockwise or counterclockwise. When you twist it 180 degrees, it's the exact same function. So rotational symmetry is thinking about it that way. How can I twist this thing? How can I rotate it so that it's the exact same function? So it's got rotational symmetry of 180 degrees. And that's it. That's the entire test review. Thanks for watching. Good luck. Hope it was useful.